Right. So last week we were talking about pressure, and as you guys said, when I go through a constriction, what happens to my velocity? How about I ask that question? What happens to my velocity when I go through a constriction? It increases. So what do I have to do? Yes, sir. Oh, so in order to get that velocity to increase, what do we have to do? It's the same as that vertical pipe we were just talking about. What happens to the fluid pressure? Does it decrease? Is that what you just said? You said decreases with a question mark, but you're right. Yeah, so exactly, right? So the example that we went through was on page 37, or very similar to page 37 in your manual. Right, and what we see there is, at position 1, we have a narrow part of our pipe. And when it goes into that constriction, what happens to our velocity? Does it increase in the wider part or decrease? Why does it decrease? Yes, you guys are correct. You're correct, Jay Ram. It decreases. Why does it decrease?
I guess because there's more space and less pressure.
There's more space, correct. Actually, what actually happens to the pressure in the pipe at that point? It increases. Very good. Right. So remember, we can't create energy out of nowhere. Right? So what we're doing is we're exchanging our potential energy, which is our pressure, basically, right, for actual velocity or kinetic energy, right? So again, now let's go back to my example of the hose, right? If you're covering the hose with your thumb, are we creating more pressure? You're creating less pressure, right? Because, well, you're not creating less pressure, but what happens is when it comes out, you're creating less area and the liquid has to speed up, right? And that's why you've now given kinetic energy to those little water molecules. They can go knock the grass off the pavement or the gunk off the dishes or whatever you're trying to do. Right? All right, do we have any questions on that before we get started with what I think is a really cool topic, but it's because that's what pays my bills. So, all right, so today we're talking about engineering statistics. So you guys all know statistics. We even talked about statistics a little bit earlier in the semester from a probability and statistics standpoint, right? Which is rolling dice, flipping coins, all that, right? You guys have that down pretty well. We already talked about that. Okay? But tonight, we're going to talk about it using a very silly example. So we all now work at a factory that makes pancakes. Okay? Probably not going to pay the bills, but just go with it. All right, so does that look like a pretty yummy stack of pancakes up there? No? You don't like pancakes? Fair enough. All right, the big butter on there is a little gross, but I'll give you that. All right, so, but here's the deal, right? We all make pancakes, and we want to do, of course, do what to our pancakes? We want to sell them to people, right? Which means we want people to buy them. So, if our pancakes are too thin, we have a problem, they burn. If our pancakes are too thick, they won't cook all the way, and then Dustin gets pancakes with cold batter in the middle, and then he wants a refund, right? And we have to give him his money back. So as a process engineer, you need to be able to tune our pancake process such that the pancakes are the right size, consistency, and so that they're just perfectly delicious. Okay? So the question is, how are you going to control your process? So let's throw out some ideas, right? What might be the variables? Right? You guys all have a general idea how you make pancakes, right? Put some flour, some pancake flour, you put some water, mix it all up, put it in a pan, cook it. Pretty simple process, right? So what are the variables that go into making the perfect pancake? Okay, the amount of batter, the amount of water. Perfect answer. What else? Cook time. Okay. What else? How much batter you use per pancake, how big the pancake is, right? But that was an interesting one, right? Because let's say we use the same amount of batter, but we pour it at different speeds. What might happen to the size of our pancake? Yeah, could be different depending on how hot your plate is, right? Which is your cook time. But do we want to bake it in an oven at 100 degrees for 3 hours? Or do we want to fry our pancake up at 300 degrees for 15 seconds before it burns? Whatever. right? So we have to consider all the variables, and that's what we're going to use statistics for, is to decide how those variables matter and how we can control those variables. So why statistics, right? It may seem silly, but statistics, doesn't matter what field of engineering you're going to go into, even the computer engineers, you're going to have to use statistics. Why do all engineers need to use statistics? It's very simple. What do you guys do as engineers? You run experiments, you run trials, you run tests, right? At the very least, you're going to run a test on something, and you need to decide whether this test is working or whether it's not. Now, sometimes that's pretty simple. Did my building stand up? Did it not, right? But now, let's say you're doing like, if a civil engineer is doing like an earthquake evaluation or something like that, maybe they're not going to just run one earthquake test or one earthquake simulation. Maybe they're going to run 100 of them, right? And then they're going to change their designs and parameters accordingly. So you have to figure out what's working, what's not. So in our example of the pancakes, what are we going to do to decide what the best pancake is? Andrew, what are we going to do to decide how to make the best pancake? Yeah, we're going to make a heck of a ton of pancakes, and we're going to eat them and sell them and whatever, right? So, like we talked about earlier, when we talked earlier in the semester about probability, we were really looking at it in terms of, you know, what die roll is going to come up. Can I go down to Vegas and win, right? That's how we were looking at it. But that's not all that statistics is, right? What we, being engineers, use statistics to do is extract meaningful information from something, right? We're going to go out, we're going to test our population, and then we're going to decide whether we like that population or we don't. And by that population, I don't mean the people who we're talking to. What I mean is the data population. Okay? So every engineer is going to have to take some sort of statistics class. Typically, like chemical engineers, we had numerical methods for chemical engineers. I know the biomedical engineers had a different class, specifically kind of tailored more towards how they'd use it. You could imagine biomedical engineers might be more focused on like clinical trials, stuff like that, right? Would make sense. But you're going to use statistics just as you would any other tool. You're going to gather information, and then you're going to analyze that information, and what are we going to do with it? We're going to use it to make a decision. Right? It's not enough just to know. We need to do something with it. So what is data? Actually, before I skip to the slide, what is data?
It's like what you record from your experiment.
Sure. What you record from your experiment. What else is data? You guys are data, right? If I were to look at you guys, how tall are you? How much do you weigh? Right? That's all data points we have to consider. Okay? So data is everywhere. School, what were your grades? How did you guys score on the test? A good teacher might look at the test and say, oh, the average was an 80. That test was too hard, assuming they're not targeting for an 80, right? They say, oh, I have an 80, but when I gave the same test to this class, it was a 90, so maybe I need to do a better job teaching period 2 versus period 3, right? So you can use that data to say, was the test too hard? Was the test too easy? Or you can use the same test to gauge different populations and decide whether or not you need to take different action based on that. And that's all decisions. So school, industry, our daily lives, right? Stocks. Do we have any stock traders budding stock traders in the class? Yeah, sometimes we do. All right. Weather, right? That's a big one. Every day we look at weather data. And a constant stream of measurements that we must summarize and interpret is data. It can come from everywhere. So again, stat basics, quick refresher. The arithmetic mean, or simply the mean, not the average, right? The mean of a data population is found by doing what? Adding everything up and dividing by the number of data points, right? So if I have 5 data points, I'll add up the value of those and divide by 5. And I'm sure you guys have seen summation notation there. I have that on the bottom. And then, what's the standard deviation? Perhaps even more important for engineers. What's standard deviation, Andrew? The mean of the differences between the data point? Okay. What about anybody else? Standard deviation? Okay. All right, so standard deviation, as defined, is a measure used to quantify the amount of variation. Right, so you nailed it, right? It's how far, I mean, the formula very fundamentally is, if you look at it, what you're doing is the value difference to the mean. So what we're looking at in this measure is how far our data falls from the mean. In other words, if I had something that was very narrow standard deviation, what would that mean, Andrew?
That would mean there's not a lot of variation.
There's a lot of variation? So, Not a lot of variation. Yeah, exactly, right? So if I have standard deviation here, everything's going to be very close. If I have large standard deviation, my population might be wide and look like this. What do we as engineers want? What's that? Small. Why do we want small variation? It's more consistent. Why do we care about it being more consistent? Count for less errors. Okay, and fundamentally, that means it's easier for us to control it. Right? All right, so now, let me ask the question, is every single pancake that we're going to make in our factory going to be the same size? No. Right, so if we're doing a bad job, we might have a pancake like this, but even if we get it so dialed in and we get every pancake just the perfect size, right, let's say like the sand dollar size is the perfect size, we're still going to have variations in thickness, width, weight, consistency, right? No matter how good we do, there's going to be some difference. So, right, so we're going to have this one here is a different shape. This guy on top is a different size. This guy on the bottom's kind of fat. He's different thickness. But the question is just how different are our pancakes? And then, do the differences matter, right? Do we think Rahul cares if his 2 pancakes are like a centimeter off? You do? All right, fair enough. You're a picky client. But if you get a pancake that's cold and not cooked in the middle, that might be a different issue, right? So applying that to industry, if we are making, let's say, screws, and we're going to put the screws in an airplane, we would like the screws to be relatively consistent. Otherwise, what happens? You might go to screw it in. One screw is too big. It doesn't fit in the hole. Another one's too small. It rattles out. The wing falls off, and everybody dies, right? Okay? So the point is, variation doesn't matter what we're collecting. When data is collected from any natural process, not all of that data will exactly be the same value, right? It just inherently makes sense. Variation, as we call it, is present everywhere. And what's interesting is the final measured value of interest may be an end result of many contributing factors, one of which may be what? What could affect variation? Malika? Time could affect it, absolutely. Why would time affect it? Yep, you're not running at the same time. I can also, like, how about if you took my height on a daily basis, or if you trended my height over my lifetime, right? That would change too, right? At the end, I get shorter and shorter and shorter and shorter, right? And what if I asked you to go out and measure something? Would you get me the exact same measurement every single time? Why is that? Because of human error. That's exactly what I was going for. Or just variations in testing method, right? Maybe you didn't. Error sometimes implies a negative, like you screwed up. But if I ask you to take a sample for exactly 5 seconds, you're going to be like 4.9, 5.1, 5.0, right? You're going to be all over the place. Okay? So the act of data collection itself is going to often introduce variation. And our job as engineers is to take that variation and reduce it wherever possible. Right, so now, I already asked the question, do the differences in our pancakes matter? Big differences are unacceptable. Small differences are fine, right? So that pancake there, the stack on the left, that's totally sellable, right? It looks delicious. Let's eat that. Pancakes on the right, I don't know that you'd want to sell that, right? Those are some ugly looking pancakes because they're not the right shape, they're fat, they're different sizes, okay? So this one's okay to sell. And this stack would get rejected, is the term we use. Right, so the pattern of variation within a set of data is called the distribution. A distribution is really just a pictorial arrangement of the data. But do we look at all the data together? Or do we look at just one part of it? So for example, would I just plot pancakes on my graph? Or would I plot size of pancake, thickness of pancake, consistency of pancake? I don't know how you'd measure that necessarily, but right. So we're going to look at size of pancake. We're going to look at weight of pancake, something like that, right? Now we're going to do this is by showing it graphically because we like to look at things as engineers and it makes sense the most. We're going to do this using a histogram. I'm sure you guys have seen histograms before. You probably made them in grade school using Smarties candies. In tonight's lab, we're using M&Ms. So we're right back to grade school. All right. What's that? No, that's fine. All right. So this histogram is generated. I actually generated this just in Excel using. I just drug it down and did 1,000 rolls of 2 dice, right? But what we see is a histogram here. Okay. So as you would expect, rolling a 1 and a 1 is the only way you can get 2, so you get less values there. Rolling a 12 and a 12 is the only way to, or sorry, a 6 and a 6 is the only way to get 12. So there's less there. But what do we see in the middle, right? 7, where there's more combinations, we see a spike. So what this histogram is showing is really just the frequency, which is the number of occurrences by bin. Okay? And what I mean by bin is what it's showing on those 2 dice, right? So I'm sure you guys have done this exercise before, and even if you haven't, it's pretty easy to conceptualize, right? You guys know statistics on dice rolls, not a big deal. And what we see is, as we would expect, over a large number of data, that we get what we expect, which is, what's this type of thing often called? What's this type of shape often called? What's that? A bell-shaped curve, right? We're getting a good distribution. But not everything looks like a bell shape. We can have different types of shapes of distributions, and they mean, of course, different things, and we can make different conclusions from them. So what we saw there was something that was not exactly symmetrical, because again, it was random data collected, but you can have a symmetrical distribution in which it looks the same on both sides from the center. You can have a skewed distribution up there on the right-hand side. What might a skewed distribution be? Can you think of a real-life example of a skewed distribution? So I'll give one, and then you guys can give me another one. So at work, we see this a lot when we're looking at number of defects on our product, right? So because usually we only have 1 or 2, but every now and then we'll have one that has a ton of them, right? So what we see is a bunch of defects that are close to 0, a big population there at 0, and then every now and then we get some high flyers that are out there. So it creates this type of skewed distribution where everything's close to one side. Can you guys think of another example? Yeah, I mean, that's probably, I don't know about that, because it depends on distance, right? You'd actually have to plot it by distance. But yeah, what do you have?
Would it be like amount of rain per season or something like that?
Amount of rain per season? Potentially. How about if, what's yours?
Test scores.
Test scores? I would agree with that, right? Especially in the classes that you guys take. Most of you guys are going to be around like 90s, high 80s, something like that, right? And then you're going to have some people who didn't study or just didn't want to be there that day, and they're going to be at the bottom of the population. That's a great example. The example that we usually use is height, right? The majority of people are going to be skewed towards a certain range, right? So within the very close distribution of height, right, you may have what we would call the bell curve. Right, everyone might be around, I don't know, in this class actually, that's probably a bad example because we have a bunch of short people and not much else, right? I mean, and what I mean is we don't have like any 7-footers is what I'm saying. But you know, if you were to go look at like the height of the school, you'd probably have a bell curve around some spot, maybe a few lows and then a couple highs, but because you guys are all growing, it's actually probably going to be skewed more towards the high with a couple of very short people, right? Maybe not a perfect example. Okay, and then a bimodal distribution. What might a bimodal distribution be in real life? And this is where we have 2 separate peaks. Can you guys think of an example in real life? No? All right, fair enough. I'm not going to keep pinging you on it. And then a uniform distribution. What might a uniform distribution be? So a perfect example of this is if you were to roll 1 die, right? You have just as much chance of rolling a 1 as you do a 6. So if you were to roll 1 die 1,000 times, it would look very similar to that, statistically. Okay? All right. Now, we already talked a bit about center. So if you have a narrow distribution, it's going to be very tight on center. And why would that be important? Consistency, very good. On the wide distribution, it's exactly the opposite. we have large variation, consistency, right? We have large variation, so you're going to be wide out from the center. And then we also have what we call outliers, right? So in this case, and that's kind of what I was talking about with defects, that's what we'll see a lot, is you'll see a lot within a population, and then all of a sudden, like, one guy's way up there, right? And sometimes you could potentially see that with height, too. Let's say most people are around, like, 5'5" to 6 foot, and then, like, all of a sudden you have, like, the super tall guy who's, like, 7'3", right? He may skew that population. All right, so let's go back to our pancakes. If we sample pancakes from our process, we can determine the distribution. So here's my theoretical pancake process distribution. So what does this tell us, Madison, about our process? What, or I should say, what observations can you make about our pancake process from this?
It has kind of a skewed distribution to the right.
Okay, so what does that mean for us? You're exactly right. More consistent in the middle? Sure. Any other observations, guys, on our process?
One somewhat outlier, but
Correct. So maybe the machine broke, or I don't know, maybe it got a bubble or something like that, right? But that one's, of course, on the high side, so he's probably too fat. And then we got a bunch of guys that are kind of trailing off there towards the small size. So the small side. Okay? All right. So we've got that. But now we know our process variation, and we can start to identify the problem's issues, right? And that's where you guys immediately went, which is exactly what I'm looking for, right? You said, oh, there's an outlier. What does that outlier mean? Oh, we've got two guys that are on that low side there. What do those mean? How come they're not on center like the rest of our stuff? Okay? And that's what we're going to be doing as engineers. So what we're going to do using this is we're going to target our pancake process. We're going to say the perfect pancake lies on that gray line, right? But the problem is our process running on target right now? You guys are shaking your heads no. Why is that? Why do you say that, rather? Why do you say we're not on target? There's not enough pancakes on each side, right? And where are the most of our pancakes? We have 5 pancakes and 4 pancakes there in the center. Where should we have those be ideally? Yeah, right around the target, right? So in this case, let's say we're creating our pancakes by doing a 4-second dispense, right? So 4 seconds of batter, 4 seconds of batter, 4 seconds of batter, 4 seconds of batter. This is telling us what?
4 seconds is way too thin. Is a bit too thin.
Yeah, 4 seconds is not enough time, right? Exactly. So what might we want to do, Rachel?
Add like a second more.
Yeah, so now we'll run our experiment. We'll increase our dispense time, keeping all other variables the same. We'll increase our dispense time by a second, and then we can see if Rachel's process is now targeted where she wants it to be. And what do we also see with those red lines that we put on there? We have too thin and we have too thick. What do those mean? Dustin, what do those mean? Yeah, but if something's too thick, what's that mean? Just from a fundamental standpoint. Sure. But what I'm looking for is we can't sell it. Right? If it's too thick, we can't sell it. If it's too thin, we can't sell it. So what do we also need to do to our distribution? Yeah, we got to tighten it up and make it more consistent. And again, with consistent, what do I actually mean? What's the word I'm looking for from a statistics standpoint? We need to reduce our what? Reduce our variation, right? Yes, you are correct. It's reduce our standard deviation, but it's reduce our variation in the process, right? So ideally, we made what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 pancakes. How many of those pancakes should be falling on either side of that target line? Well, 16 is what we hope. We hope that all 16 fall within that sellable region, right? Because then we're making the most money. So if I ask the question again, is our process okay? It's okay. But what can we do as engineers? We're not going to make any money being okay. We got to improve that process. So the answer is no. we need thicker pancakes. What we really want to do is to target our process so it falls right about there. Right? Let's put that line on 5. Let's just figure it out, and we'll move our process up. So what we can do is we can apply Rachel's fix, or proposed fix, which is increase the dispense time, which I think is a great idea. But we also need to do what? We need to tighten up our distribution so that we don't have that. Because see, even when we move our process, we've got a guy that's too fat, and we've got a guy that's too thin, and we're throwing product away. We're losing yield, we're losing money. So we should also try to reduce the spread or reduce the variation. Okay? All right. So what we can do to look at this process, or any process rather, is we can calculate what we call the summary statistics. 2 of those you already know. The mean, and what else? Mean and what? Standard deviation, right? The variation, okay? So, a quartile, does anybody know what a quartile is? What is it? Andrew, you're nodding your head. What's a quartile? It's the quarter. Fair enough. No, so what, yeah, what is it?
Isn't it like a certain amount of standard deviations away from the middle?
So that's the next step, and that's called a sigma, but you're right on it, right? So quartile is literally if we divide the data population, let's say we have 100 points, say we have 100 data points, how many points would we expect to be in quartile 1? 25, is that right? Yes, that's correct. How many in the second quartile? How many in the third quartile? And how many in the fourth quartile? You sure? Okay. But so all we're going to do is we're going to line them all up from bottom to top in ascending order. We're going to cut the bottom 25, second 25, next 25, next 25. Okay, so in this case, you guys have all heard the term the median, right? The median falls at the 50th percentile. Now, if my population looks like this, is my mean and my median the same thing? No, and why is that?
Because they're supposed to line up if they are the same.
They're supposed to line up in a perfect world, yes. Right? If your data population is perfectly, does anybody know the answer? If our data population is perfectly what? What's that? If it's perfectly centered? Okay, but then you could, I mean, in this case, we still have a skewed, right? All right, but quartile is simply a percentile of the data set with divides it into 4s, okay? And then we use those quartiles to find the median, okay? The reason, though, that we care, aside from just saying median and then moving on, right? The reason we care is because we can generate box plots for it, okay? So what we can do in a box plot is it serves, and what I've done is I've drawn this box plot horizontally, and a lot of the times you're going to actually see it vertically, and actually not a lot of times, like 99.99% of the time you're going to see it vertically, right? But what I've done is I've drawn it horizontally so that you can view it over top of a histogram, over top of a distribution. Dustin, can you see okay? Probably not, right? You can? Okay. All right, so on this side, we draw a line on the box plot to note the minimum. That's the very lowest point. Okay, then we draw a line at Q1. We draw a line at the median. Now note that that's not exactly in the middle of the box. It's wherever the median is, right? A line at Q3, and then a maximum. And then we draw, for the box plot, we create a box that is in the middle 50%, the middle 2 quartiles. Okay? So what this looks like in a symmetrical distribution, it looks nice and pretty. You have this nice box here. 50% of the data is here. It shows the minimum, shows the maximum. But in a skewed distribution, then it looks something like this, right? Again, 50% of the data population is here. That 25th percentile, there's still 25% of the data there, but it's all scrunched up in there. And then we've got these guys all the way out here because so few of the data is here that the top 25 is hugely spread out. Simple enough? All right. Now, why might we care? It's because we can use box plots plotted side by side to very easily identify differences in distributions, right? And I'll be honest with you, I am looking at charts like these probably 50 times a day, every day, doing different comparisons of our process and looking at it. So, in the example below, a factory manager or a process engineer might use something like this to compare the factory's performance to another factory in a different state. So in this case, let me ask you, Lynn, which factory has the tightest variation? Why? Right, so factory 2 has the lowest variation because the box plot's the tightest. Okay, so again, when our box plot goes from minimum to maximum, if you have a wide distribution, it's going to be a very large box plot. If you don't, it's going to be a very tight box plot. Okay, what do we see about factory 3? Does anybody have any observations about factory 3? What do you think, Dustin? Everything's really different? Is it though? So this is a tricky one. I'm kind of picking on you, but this is a tricky one. Yeah, they have a lot of, exactly. So it's a very wide distribution itself, but what do we notice about the middle 50%? It's pretty tight and it's pretty equal, right? So what we're seeing here is we're seeing a data population that's very tightly grouped in the middle, but you have some guys that are way outside, right? So this guy is still probably that factory number 3, is still probably producing a large number of sellable pancakes in this case, but has pancakes that are way off from time to time. So what you would, as the pancake engineer in that factory, would need to do is go figure out why you're creating super bad pancakes, right? You've probably got your process dialed in well, but you've got these outliers. We need to go solve the outliers. And then what about factory 1? Any observations on factory 1? What do you think, Thomas? Mm-hmm. Yeah, I mean, again, that's, assuming the target, right? We don't know where the target is. We don't know what the desired outcome is. But factory 1 looks pretty good. Factory 2, of course, is our best. And factory 3, of course, has some work to do. Again, they're not doing a horrible job, but they've got some work to do. Okay? So if you guys could go, please, to page 45 in your book. You guys are now engineers at Intel, working in the lithography group. 4 spin coating tools within the same factory are compared. The desired thickness target is 1 millimeter, which is drawn in on your graph. The question is, which tool is running the closest to process target, and which tool has the most consistent performance? And then at last, as an engineer, you must decide which tool is the best, because we're going to take all other tool settings and adjust it to that one. So which is our best tool, or your golden tool? Right, Elizabeth, you got it? You think so? Hope so? Fair enough. All right, so Elizabeth, nice and loud so we can hear you. Which tool is running closest to process target? Coder A? Does everybody agree with that? Disagree with that? Okay, so we have coder A, which we believe is running on target. Do I agree? All right, so I agree. I think that coder A is running closest to target, but is coder A our best tool? Why? It's running on target.
My variation.
Variation, okay. So now then I asked you the second question, which is which has the most consistent performance? Which tool has the best performance? D, because it has the tightest distribution. I agree. So now the million-dollar question, because you as the engineer are now going to make a process change. You're going to change all your other tools to match so that you can increase your money. Which tool do we match to? Izzy says D. Why do you say D?
Well, I mean, coaster A is like on the point, but it has a wide variation, so you're still losing money on the outliers, while coaster D is pretty close to it compared to all the others, and has a tighter variation, so you're most likely to still get into that box, or as close as you can to the 1 millimeter. Okay,
fair enough. So Izzy, the process engineer, is going to dial in everything to D. Does anybody have any other ideas? Everybody agrees? All right, I agree as well. You just got promoted. Nicely done. Yeah, so coder A is not a bad target, right? We're still selling stuff. but we can do better. And then the bonus question, Izzy, is what might you do next? So this week you selected which your better tool was. Now what you might do, what might you do next week?
I'm trying to get it, change it a little bit.
Okay.
To test if you would do some trials and see on these different modes to see where it would land, and then try to pick the best mode for coaster D. So using the same tool, but seeing out different variations of
So I mean, what you said was that Coder D looked great for variation, but it was slightly off target.
Yeah.
So what are you going to do next week?
I'm going to try to tweak it so I get as close as I can.
Heck yeah, you're going to get it back on target. Heck yeah, perfect. All right, so we found the best way to run to get variation down. We locked in the goodness, and now we're just going to dial it down and get perfectly on target. Coder. So it's a spin coder. The way it works is it spins the wafer really, really fast, and they deposit goo in the middle. Basically, in this case, we're depositing, the reason I chose spin coders, because it's very similar to making pancake, right? So we're spinning our plate. We're putting a little pancake batter in the middle. What it does is it spins the pancake batter out in a perfect circle, and you get a nice even coating on your plate, right? It's the same idea. Okay, so let's compare our pancake machine settings. So we did 3 experiments. All right, and you're up, Rahul. We did 3 experiments adjusting the speed that the nozzle puts out batter. So we have pancake thickness. Now we have a target to go off of. All right, setting number 1 is there on the left. Setting number 2 is super tight, but what's the problem with setting number 2, Rahul? Really far off target. And what about setting number 3? How does it look compared to number 1?
A lot tighter.
It's tighter? Oh. Still off target? All right, so the question is then, you're our pancake engineer, your pancake process engineer. Which process do you go with? And why?
I go with 2 because it's already a lot more consistent and be a lot easier to tweak it so that it reaches the target since it's already performing.
I see. So you're going to use, I see what you're saying, but in this case, right, all we're doing is adjusting the nozzle speed. Right? So in this case, which nozzle speed would you choose? The third one. And why the third one?
Because it's on target and it's pretty consistent as well.
Yeah, so I agree. As your pancake process manager, I agree. I think we go with setting number 3. Because even though it's slightly off target, it's better and it's really close to target. And now you may come back next week and you may say, okay, now that I've got my batter dialed in, let's adjust my batter consistency, and then maybe you can figure out how to get setting number 2 up or something like that, right? But when you're looking at just this variable, just this test, just making the one variable change, I think you go with number 3. Okay. All right, so time trend charts, and this goes back to what Malika brought up, right? Which is Andrew getting older and older over time, right? So what we've done so far is we've looked at processes snapshotted. But anyone here drive a car? I know Izzy does, right? What happens to your car over time?
It gets worse.
Gets worse? Okay. What happens to your tires? Your tires wear, you get gunk in your engine, you need an oil change, right? All that stuff, right? So, and in this case, that's actually what I'm looking at, right? We're looking at a time trend of miles per gallon. So what do we see if we look at our miles per gallon over the course of a year? What's happening very clearly to our miles per gallon? It's declining, right? Our car's aging, it's becoming less efficient. But here's the trick, right? If we plot, so we all agree 100% that we have a time trend, right? We have a decreasing, and by time trend I mean it is trending over time, right? It's changing over time. We all agree on that, right? But look what happens if I plot this data over time on a histogram. That histogram looks pretty darn good, doesn't it? Looks like a very consistent process. But is our process actually consistent? No, our car is not actually consistent. And in theory, if we let it go forever, we'd eventually not get anything, right? That's not the way you want to run a factory. Because now let's apply this to our pancake factory. If our pancake factory was trending over time, what happens when we say, okay, we got our process dialed in, let's all go on vacation. We come back from vacation, and what happens? Yeah, we're making bad pancakes. We all just lost our jobs, right? Okay? So in this case, if we were to use just a histogram, we actually don't gather all of the information that we need as engineers to make a decision. So we have to use time trends as well, right? We have to look at it over time. So time trend, we also call it a run chart. Does anybody know why we call it a run chart sometimes instead of a time trend? Okay, so let's say that I have Malika, right? You're my data collection expert, right? You're going out every single day at the same time every day and you're collecting data for us. In that case, we may be able to do a time trend because it would show it trending over time. But what happens if I'm sampling random parts? Like say we're making pancakes again. And one day I sample 3 out of the same batch, and then I wait a couple days, I sample another batch, sample another. Can I get a time trend from that? Kind of. But it's going to look really weird. I'm going to have 3 points and 1 and 1. So in that case, what we're going to do is we're just going to do a run chart. We're going to say sample 1, sample 2, sample 3, sample 4, sample 5. And that way you can still get a time trend without actually having the time be the x-axis, right? It just helps it be easier to look at. Okay? So what we're going to do is essentially what we did in the miles per gallon plot. All we're going to do is plot the data versus time or versus run. We're going to connect them with lines, right? No different than making a scatter plot that you guys have probably done 100 times in Excel. Or Google Sheets actually is what you guys mostly use, right? The reason that it's important to look at the time trend is to look for stability, right? What we want is a process that's stable over time. What do I mean by stable? It's consistent, okay? So in this case, what do I mean by consistent? It's not changing over time, right? So a data set said to be stabled when all measured variables have a constant mean and constant variance over time. So in other words, my mean's not changing, my plot's not drifting, and it's also not getting wider. Okay? And the distribution of that variance should retain the same shape. So if you go to page 46, in your manual, what you're going to see are 4 different plots. And I'd like you to tell me whether those plots are stable or unstable. Not stable. Unstable. All right, so Madison, is plot A, is it plot A or plot 1 in there? Plot A, is plot A stable? You say yes? I agree, it's stable. And why is it stable? Stays consistent, so it has even mean. It doesn't get skinnier or fatter over time. It looks pretty good. We've got a nice pancake trend there. We can go on vacation. All right. Chandler, what about plot number 2? Is this guy stable? You say it's unstable? And why is he unstable? Yeah, at some point, the data set lost its mind, didn't it? This guy, now what's interesting is this guy maintains roughly the same mean, would we agree, if we were to plot just the mean over time? But at some point, at about data point, 26 or so there, something in the process broke and we started shooting out fat pancakes and thin pancakes and not good pancakes, right? So I agree, not stable. All right, J-Rom, how about this one? C.
I would say, I don't know, I was guessing unstable because it seems like it's all over the place.
Okay. So this one, and I picked on you because this one's undetermined. I couldn't tell from this one whether it was stable or unstable. So what in this case would we as engineers do? What's that? Heck yeah, you keep running. Sample more, you watch it every day. Instead of, right, chart A, you might say, oh, I only need to look at chart A maybe a couple times a week. Chart C, you're going to come in and look at every day and maybe even huddle with your team and have a discussion about it every day and see what we need to do. All right. Who's left? Who haven't I picked on? Dustin, what do you think about this one? Mostly stable? All right, this guy I think is not stable. His mean is changing over time, so he's pretty consistent in terms of variation. His variation's the same over time, but his mean is moving all over the place. And again, this is one of those where if you were to look at this guy on a histogram, he'd look amazing, right? He'd look like a perfect bell curve probably, but over time he's definitely not stable. All right, and then we keep using that term, the bell curve, and that's what we're looking at. So the normal distribution is what we call that in statistics. is the most well-known distribution. You guys have probably all seen this many times before, right? Real-world examples include heights, object produced by a machine, that's a key one, and even errors in measurement. So the figure above shows a normal distribution, which is the black line, and that's actually a mathematical normal distribution plotted, versus a histogram which roughly follows the normal distribution. And they pretty much fit. Now, why do we care about the normal distribution? Does anybody know why the normal distribution is important? Any ideas? Other than just I'm telling you that? Okay, so what you said was if something doesn't follow the normal distribution, you might want to look for reasons why. Okay, I agree. That's a good one. Okay. Now again, we talked about it before. Maybe you could have a skewed distribution or something based on your process, and that would be fine. But largely, the reason we like the normal distribution is because it's a perfect mathematical theoretical construct. Okay? So in the normal distribution, 50% of the data falls below the mean. And in this case, what is also the mean? The median, right? The mean and the median are the same in the normal distribution. And that's the big deal, right? So 50% fall below, 50% fall above. In the normal distribution, the mean is equal to the median. And now we go to Malaika's sigmas, right? That's what we call them. So the theoretical normal distribution has the following characteristics. Roughly 68% of the values fall within what we call 1 sigma, which is 1 standard deviation above the mean and below the mean, right? So what I mean is if I take the mean plus a sigma, plus a standard deviation, or the mean minus a standard deviation, within that range, 68% of the data falls within that range. Okay, for 2 sigma, 95% of the data falls within 2 sigma, 2 standard deviations plus or minus on the mean. And 99.7% of the naturally occurring data in a perfect distribution, or in the normal distribution, falls within 3 sigma of either side. Has anybody heard the term 6 sigma? So 6 sigma is a certification that you can get, and like it's an industry, a lot of process engineers get it. 6 sigma is 3 sigma below plus 3 sigma above, right? It's basically, the 6 sigma is 99.7% of your process. So for all practical terms, your process, when behaving normally, should fall within 6 sigma. 3 standard deviations either side of the mean. Okay? And it's essentially a quality control and process improvement certification that you can get. All right, so now, you guys might want to write these down real quick, just so you can remember. So 1 sigma plus or minus is 68. 2 sigma plus or minus is 95. And 3 sigma plus or minus is 99.7. Okay, so on page 47 in your book, if 95% of the bolts that are being measured are found to weigh between 1.1 grams and 1.7 grams, assuming a normal distribution in our process, which of course we do, calculate the mean and standard deviation of that process. So I'll give you guys a couple minutes. All right, so just to clarify, what we did here is we measured 100 bolts, and 95% of them fell between 1.1 and 1.7. So what numbers might we be looking at here? What's that? Right, so but 95%, what does that line up with? 2 sigma. So what would we use that information to determine? Sigma. Very good. Andrew, you're my man, right? You got it? What'd you get?
I got a lot of pressure. I got 1.4 for the mean and 0.15 for the...
So 1.4 for the mean and 0.5 for the standard deviation? 0.15 for the standard deviation? All right. So real quick, why don't you walk us through the strategy that you used to do this?
Well, I knew that since it was 95%, I knew it was 2 standard deviations away from the mean. So I I mean, I just assumed that the mean was 1.4, and then I knew the difference between 1.4 and the two like endpoints, I guess, was 0.3, so I just divided it by 2.
Okay, I think that was a really good way to do it. So let's see what I got. All right, so I did it very similarly. I said 1.1 plus 1.7 divided by 2 equals 1.4, because that's the mean. And then 95% falls within 2 sigma, which means that we can divide the difference by 4. 0.6 divided by 4 equals 0.15 grams. So I get a mean of 1.4 and a sigma of 0.15. Nicely done, sir. Excellent. All right. So that takes us to the engineering application side of this, right? So we've got the math down, we've got the understanding down. You guys can look at a graph and tell me whether it's a good graph or bad graph. All right, so now you can come work for me for the first 2 years, but after that, we need to do more, okay? So we're going to go to statistical process control. This is a tool that we use to actually start controlling and monitoring the health of our process. So statistical process control, or SPC, is a method of process monitoring and quality control, like I just said. All this is a series of, right, this is not a difficult thing. All it is a series of tools and methods for controlling our stability of a process. Because again, once we control stability, we can control the target, we can control the variation. We have 2 terms in SPC. We call our process either in control or out of control. And the ultimate goal of SPC, statistical process control, is rapid detection when something goes wrong within our process. How we do this is we define and look for what we call rare events. So remember, what percentage of my population falls within that 6 sigma range? 99.7%, which means that how many normal points fall not within that? 0.3, right? And that's 0.3%, right? So that's a very rare occurrence that a normal data point falls outside of that range. So what we look for in SPC, as a general rule, is we actually expand it a little bit, but we look for an event that is statistically likely to occur less than 1%. Okay, so if anything, if we ever measure a data point that occurs, or that should occur less than 1% of the time, we say, whoa, stop, let's go in and figure out what happened with our process. Did something break? Did something shift? Do we have a problem? And then we shut it down so we're not making bad product, right? Because it doesn't do us any good to produce a bunch of bad pancakes, because then what's going to happen? We're throwing them in the dumpster, we're taking them down to the homeless people, right? We're not making any money off that, okay? So, now remember, a rare event is less than what percent? 1%. All right, so on page 48 in your book, using your normal statistics that you guys are quite familiar with, I would like you to look at the 4 events below and tell me whether they are a rare event or not. Number 1 is flipping a coin and getting 3 heads in a row. Number 2 is flipping a coin and getting 8 heads in a row. Collecting a sample that is greater than 3 sigma away from the mean and normal. And number 4 is collecting 8 samples in a row that are below the mean and normal. Rachel, you going to do this one for me? Will you do this one for me?
Sure.
Sure?
Number 1?
Okay, so you said number 1 is not rare because it's what?
1 out of 8.
It's 1 over 8?
1 over 8, yeah.
All right, so yeah, I did 0.5 to the third, which is 0.125. Yes, you're correct, which is 1 over 8. How about number 2?
Number 2 is rare because it's 1 out of 196.
Okay, so I agree. So in that case, I did 0.5 to the 8th, which is 0.0039, which is way less than 1%. So that is a rare event. Now, how about this one? You don't even need math for this one. What is the chance of collecting a sample greater than 3 sigma away from the mean and normal distribution?
You already gave us the thing, which is 99.7.
Right. So what's the chance of being outside of that?
0.3%.
And is that less than 1%?
Yes.
Yes, it is. So that would be a rare event. And how about collecting 8 samples in a row that are below the mean in a normal distribution?
I guess not rare, but I'm not so sure.
Okay, so interestingly enough, this is actually the same calculation as number 2. Because remember, below the center line is 50%. So it's the same as what we did for number 2, collecting 8 samples below the center line does actually flag as a rare event. So let's put that into perspective on what we're going to do for our engineering application. So we're going to create something called a control chart. Now a control chart is really just a trend chart, right? It could either be a time trend or a run chart, either way. But what it's doing is it's trending our data. And very similar to how at the very beginning, remember we put a target and we put bounds on our pancake process? That's all we're doing here for our control chart. Okay, so we're measuring our data, and what it's going to do is if the point is in control, if it's behaving as it should be, it's going to be green. So we're trucking along, we're making data here, and all of a sudden we measure a point down here. This point is out of control. So what would happen here is it would log our tool. So at Intel, what happens is it logs our tool down automatically, flags the engineer. The engineer goes in and figure out, is it broken? Was it just a bad measured data point? But we go in and we investigate. We stop producing product on that piece of equipment until we can get that fixed or get it solved. Okay? And then we bring it back up. It's running well again, and everything's okay. But what we were going for on the last one, right? So remember, we said that 50% of the data population should fall on either side. So if we were to look at this over long term, how many, let's say we take 100 points on this chart, how many of those points would we expect to be up here? 50. And how many of these points would we expect to be down here? 50, right? So in the example I just had you guys do in the book, if we were to ever get 8 of these, so there we have 1, 2, 3, 4, oh, but he hit center line, we're okay. 1, 2, oh, we're okay, right? If we were ever to get 8 of them consistently in a row on one side, we would also flag that point as being out of control. So in that case, this guy, let's say there were 8, this guy would become red and out of control, and it would flag the engineer to go look at it, even if it was inside the distribution, but because that was a rare event. And the reason that might be a rare event is, let's say the process shifts, but not enough to go out of control like this guy, which is outside the sellable limit. You still want to know that your process shifted, because now, if your process shifted, let's say our process moves from here to here, now we could be producing a significant amount more of unsellable product, even though our process is still trucking along, but now we're selling more our bad stuff, right? Does that make sense? Okay. So what we've done is, A, we've put control limits on the process. Now again, we talked about 6 sigma. We talked about our process. So our upper control limit, we're going to set at mean plus 3 standard deviations. And our lower control limit, we're going to set at mean minus 3 standard deviations. Right? Makes sense. It's just creating our normal distribution. So in our pancake example, we're trucking along, we're making green pancakes. All of a sudden, one of our pancakes comes out too thin. We need to stop. We need to go back. Rahul needs to test and figure out whether the nozzle's jammed or whether a bubble came out or what, and figure it out, adjust it, fix the tool, and go accordingly. So the question here is our process okay? What do you think, Jairam? That's what you got? You got an out of control. Is our process okay? Sure. I mean, the answer is, as long as you know what happened, it's okay, right? If your tool goes and breaks, you don't have to retarget your process. You just fix your tool, bring it back up, and run the tool. Okay? So it's stable, but of course we need to investigate what happened. So again, and I'm not gonna hide the book, but what we've done for statistical process control is we've gone through and we set up a bunch of rules. Now all of these rules, remember we talked about the rare events, that's what I had you guys calculate. All of these rules lead to something that statistically happens less than 1% of the time. Right? So, like we talked about, only 0.3% of the time will something fall outside of the normal distribution. So in that case, number 1 is an OOC flag, is what we call it. We then have number over center line that we talked about, which would flag an out of control point. And we also have this one, which is the bane of my existence, which is 2 out of 3 consecutive points. This is a mouthful. 2 out of 3 consecutive points are more than 2 standard deviations away from the center line and on the same side. So we call that 2 out of 3. 2 out of 3 sigma is what we call it from shorthand. But what it's essentially showing is that our guy's going okay, but all of a sudden, boom, boom, boom. right? That will statistically happen 1%. And here we get boom, boom, boom. So the gray line is not out of control. The gray line is your 2 sigma. So if we ever get 2 points out of 3 that are outside that, that's statistically less than 1%. So again, we flag the process and we can bring it down and investigate. Okay, any questions on that? All right, this is my lifeblood. Again, so you guys all just completed this course. You guys are all experts on SPC. You can all come work for me now, right? Perfect. All right, that is the end of the lecture. So what we're going to do for tonight's lab is, like I promised, we have candy. Now I have to ask the unfortunate question, is anybody allergic to chocolate and or peanuts? Yes. All right, nobody's going to die on me, right? Everybody can eat chocolate and peanuts? All right, perfect. All right, so let's take a 5-minute break. Let's come back, and we're going to make some candy control charts.